Okay, we are here to look at uniform motion. So let's take a look at it here. When we're talking about a uniform motion and uniform acceleration for motion, so far we've talked about velocities and acceleration. And we've talked about how a velocity can be equal to some displacement divided by some amount of time. This is a vector. And we've talked about how acceleration, this vector, can be equal to a change of velocity, a final minus an initial, divided by some amount of time here. So far we have these two equations. We have a constant or average velocity, so up here our acceleration for equation 1 is 0, and down here our acceleration is constant. Well, it turns out if you expand on this, if you don't have just a constant velocity, but you have a velocity and you are accelerating, so maybe you're traveling down the road at 35 miles per hour, then you step on the gas. You had some velocity, and now you're stepping on the gas. You're going even faster, or maybe you're hitting the brakes. How far are you going to go after you hit those brakes before you come to a stop? To do that, we have expanded or derived equations for this. So if we take a look at them here, we can see that with these equations, we have a few more forms. We've got equation 3, 4, 5, and 6. And these four equations here, they all deal with velocities, final and initial, an acceleration, a time, or a displacement, as we see for a few of them. And these are the equations that we can be picking through in order to look at how an object with uniform acceleration, so speeding up or slowing down, will be moving and how we can kind of map its motion. It is important to recognize that equation 2 and equation 3, they are actually the same equation. They're just written a little differently. If we multiplied by time over here and then added a VI to both sides, so it went away and we put a VI over here, we would just get equation 3. So really, if we have the acceleration and it's not equal to 0, we can use the four equations over here. But when acceleration is 0, we're stuck just using equation 1 on the left-hand side, okay? So these are our motion quantities here. Now, in regards to these motion quantities, there are quite a number of them as we see. We've got a displacement, a final velocity, an initial velocity, an acceleration, a time, and what did I say there? Yeah, 5 of them. Now, if we have ever 3 of these quantities, let's say we've got VF, VI, and A, we can always solve for both other quantities. So if we've got 3 out of the 5 things in this list, we can technically solve for all of them. We might have to use 2 equations, but we can technically do it. Okay? The hard part about this is figuring out which 3 of the 5 do I have and which equation should I be using. Should I be using equation 3, 4, 5, or 6, or should I just be using equation 1 if the acceleration is 0? So that's the actual hard part of physics. Which equation should I be using here given what I have? So let's roll it over to the equation picker here. The equation picker will ask us, it'll say, look, you've been given 3 things. Okay, so if we look at our first one here, given a final velocity, an initial velocity, and a time, and we're looking for an acceleration, that's our unknown, what equation would we use? So if we go over to all of our equations over here, and we'll clean this up a bit. If we take a look at all of our equations, we have a final velocity. So I will just go through and highlight all the final velocities. We have an initial velocity. We have time. And we're looking for an acceleration. So which equation should I be using here? Well, I can't use equation 4. It doesn't have an acceleration in it, so I can't find an acceleration. If I look at 5 or 6, oh, 5's got acceleration, that's nice, but I don't know what this delta x is, which means there's 2 unknowns in this equation, and I can't solve it. Because remember, for one equation, you can only have one unknown variable. You need multiple equations if you have more than one unknown variable. You need one equation for each unknown. The same thing applies to this last one, number 6. I still don't have delta x, so this one goes away. If you look at 3, I have VF, I have VI, I have T, I'm looking for A. This is the equation I'm looking to use here. I can plug in my given constants or my given values, the 4, the 32, the 5. I can play some math, and I can go ahead and solve for that acceleration, whatever it may be. Okay, so let's take a look at one more here. Let's just practice one more time. together, and then we'll pause the video and then we'll try the rest of these. So if we're given a final velocity, these are our finals again. If we're given an initial velocity, and let's highlight all the initials, and we're given a time. So we're given the same things as we were last time. Okay, that's cool. But this time I'm looking for my unknown of a displacement, a delta x. What should I be using? Oh, I actually missed a time here. Do you see this? This one's real clever. That one's hidden. We've got a time and time squared. Those are both times though. Okay, so we gotta be careful there. So what should I be using here? If I'm looking for an unknown x, well, equation 3 looks pretty nice, but it doesn't have a delta x in it. It doesn't have an x. It has the a, which I had last time, so 3's out. Could I use 4 here? Well, it's got VF, it's got VI, it's got T. That's everything. So I actually really like equation 4. Equation 5 is missing the acceleration, so it's out. And equation 6 is missing the acceleration too, so it's out. So yeah, equation 4 is what we want here, okay? So run through this real quick. See if you can figure out what all of these are. You know, just pause the video, kind of take some time and work through this, because you're going to be using this best friend we have here, these derived equations, a lot. And if you're looking on where you can find this sheet for the derived equations, if you have access to our Canvas page, these derived equations that we have here, if you go into Unit 3 and you go into Objectives, the Objectives section there will have this screen. It's the CP Unit 3 motion quantities with all the different items we're going to be looking at, but down here we see all of our motion equations that we want. And I like to call this our best friend, because we will be using this a lot going forward in this class. We're going to be using it all this unit, all the next unit, and all the unit after. So this is your best friend. Definitely take a picture of that, save it to your computer, write them all down, put them on your wall, put them everywhere, okay? Put it on your turtle shell, because these are very, very important moving forward. So take a second, pause this video, see if you can answer 3, 4, 5, 6, 7, and 8, and then we'll take a look at what's going on in that for a second, okay? So while you take that picture, I'm gonna look while you take a second to pause this video and try these out, I'm gonna look very stoic. Did you pause? Because I can't hold this all day. You gotta pause to get this face. And you should have been doing these problems. Okay, so now that we're back, because you paused and you tried these out, right? Because if you didn't, what's the point? Let's just take a look and run through these very quickly for what we've got here. So let's see. I've got a VIT and an X. I've got an unknown A, so that's VI, T, and an X. This one doesn't have an A, so I can't use that. I got a VI, a T, and an X, and I'm looking for A. Boom, it's 5. Gotcha. Let's see, for 4, given VF, so I've got a VF, I've got a VI, I've got a delta X, and I'm looking for an A. Notice how in 4, T doesn't pop up. There's only one of these equations that doesn't have a T in it. It's number 6, so I have a feeling I'm going to go there. And if I take a look at that, yeah, I've got a VF, I've got a VI, I've got a delta X, I'm looking for A. This is number 6. For 5, VF, VI, and a T and an unknown A. Well, this looks very similar to what we did up top in number 1. They're actually the same, givens and unknowns. So this is going to be a 3. And if you're also looking and saying, hey, look, I put a number 2 for that. Is that all right? Yeah, because remember, 3 is the number 2. These equations are the same. So however you're putting that down, doesn't really matter. Let's look at number 6. Given an object is at its max height. What? It has an initial velocity of 2 meters per second, and the unknown is t. Well, for unknown is t, it can't be 6. Okay? We also know we have an initial velocity, so, well, that's not helpful. All of them have initial velocities. But an object is at its max height. Well, now we got to think as physicists about what does it mean for an object to be its max height. We'll talk about this in a little bit more of motion, but if an object's at its maximum height, it's not moving. If you think about just take an object in front of you right now and toss it up, when it gets to that maximum point, it kind of pauses for a second, okay? Just for a moment's time, just for a very instant, but it kind of floats there for a moment. And on that float, that is the change of direction of an object. So that's when the object is going from up to down. So here's the object going up, and here's the object going down. And when it gets to that top point, the velocity is 0. And this also makes sense if we think back to our velocity graphs we did a little bit ago. Here were positive velocities, here were negative velocities. If we have an object that is constantly slowing down at a uniform acceleration, well, it's slowing down, slowing down, slowing down. It still has a positive velocity, so it's moving up, but it's slowing as it comes back to the x-axis, which is going on here. When it crosses that x-axis, as we saw, it has 0 velocity, and that is the top of the object's height. So we actually know here that when an object is at max height, its final velocity is 0. So we actually have a final velocity here. So we've got initial, we've got a final, we've got a, what else do we have here? Oh, we're looking for an unknown t. So we've got an initial, we've got a final, we're looking for an unknown t. But what is this acceleration? Well, we know this too. It's gravity. Okay, when we toss an object up, what's causing it to slow down and then fall back down? What's causing you when you trip to fall and smash your face on the ground? That's gravity. And we know quantities of gravity. Gravity has a constant value on Earth, on the Earth. It changes as you move away from it. But we're going to say that that value is negative 9.8. And it's very important to recognize here that that negative is just representing down. Okay, if you call down positive, then that'd be a positive 9.8. But because of this, we know the acceleration. We know the acceleration here is negative 9.8 meters per second squared, which means we know an acceleration, we know a final, we know initial, we know we're looking for the unknown t. This one is 3, or 2 if you like to put that. So that was a hard one there. We had to really think as physicists to find some unknown quantities that we actually did know. Okay, they just weren't given to us right off the bat. For this one, for number 7, a car's driving 14 meters. So if it's going meters, that's a delta x right there. It has an initial velocity and has an acceleration. I'm looking for a final velocity. Well, let's take a look at all of our equations here. Let's clean these up a bit. If we have a delta x, here are all our delta x's, so this one's gone. We have a vi, so here are all our vi's. And we've got an acceleration, a. And we're looking for VF. Whoop. Well, this doesn't have a VF, and this probably has a VF. We don't have the time, so it's gone. We're left with number 6. We could rearrange that and find it. Okay, and last one. An object falls through the air 20 meters. Oh boy. Okay, so this is a delta x. This is one of those like worded ones again. And then here's a VI. So I've got a delta x and a VI, but that's only 2 things. I need 3 things here. Well, if the object's falling through the air, what's causing it to fall? We know that the object's falling due to gravity. That's that negative 9.8 meters per second squared. So we have an acceleration, we have a delta x, we have vi, we're looking for t. So we could go ahead and use equation number 5, because we have delta x, that's 20, we've got vi's, we've got the acceleration, and we're looking for t. Now, that's a little weird though, because if we take a look at this one, and we do this here, where we fill in the values, we're going to have 20, and I'm going to put a star next to that 20 real quick, and that's going to equal the initial velocity, which we say here is 6.5 meters per second, times t plus 1/2 times negative 9.8 meters per second squared, times t squared. And since this object is falling through the air, it's actually going down, and we called down the negative direction. See how gravity is negative there, and gravity is pulling down or inward towards the Earth. So we actually need to have a negative here. But this equation is kind of weird, because how would you go ahead and solve this equation? It has a t and it has a t squared. Here's how we go ahead and do it. We can solve this equation using the quadratic formula. And if you haven't checked out my Billy Joel rendition of Quadratic Time, you should definitely go check that out. But if we use the quadratic formula, we can reset that equation we had before. We can take this equation here, and we can set everything equal to 0. So I'm going to combine the 1/2 and negative 9.8 to get negative 4.9t squared plus 6.5t, and the minus 20 is going to be positive when I bring it over to the other side, so plus 20, and this equals 0. What I'm able to do then is look at the coefficients. These are the numbers that sit on the outside, a, b, and c. These three coefficients here, a, b, and c, these numbers allow us to solve a quadratic equation. And if we take those numbers and we put them into the quadratic formula for a, b, and c, we can go ahead and solve this. So if, let's just rewrite this out here, a was equal to negative 4.9, b was equal to 6.5, and c was equal to positive 20. If we go ahead and solve this, we're actually going to get two answers. And I encourage you to try to solve this on your own calculator here, because if you have to use a quadratic formula, and you'll only ever have to use it in equation number 5, you'll only have to use it in equation 5 when you're solving for time. It's the only time you'll have to use it. But if you have to use it, how do we do that? So we're going to get negative 6.5, and then we'll do the plus first. This plus minus here means there's two answers. One's a positive, one's a negative. So we'll add first, so plus the square root of the quantity b squared, so 6.5 squared, minus the quantity 4 times a, which is negative 4.9, times c, which is 20, all divided by the quantity 2 times a, which is the negative 4.9. And when I do this, I get a first value of negative 1.46 seconds. Okay, let's do this again. Let's do it with the minus. So wait, did I do that wrong? I have a feeling I might have messed something up. Check my math. That might be a positive. I'm going to run that again. 6.5. Oh, no, I did that right. Yeah. It's negative 1.46. Whew, I was worried for a second. I was worried. So negative 6.5, because the minus of b, minus this time the square root of b squared, so 6.5 squared, minus the quantity of 4ac, so 4 times negative 4.9 times 20, divided by 2a, so that's going to be negative 9.8. That's 2 times negative 4.9. And we get a value of 2.78 seconds. At least that's what I got here in my calculator. That should be right. Now, here's the weird thing about physics. In math, those are the two answers here. But in physics, one of these answers is wrong. What? But math is never wrong. Math is physics. If you take a look at these answers, have you ever measured a negative time? Have you ever said, yeah, it took me negative 3 minutes? No, because if you had a negative time, that's like you went backwards in time. And you can't go backwards in time. So this is a non-physical answer. Okay, it's non-physical. It is a number. Mathematically, it is a solution to this problem, but it doesn't make any sense from a physical standpoint. It is a negative time. You're going backwards through it. It just doesn't work. Okay, our only true answer that we have here is the 2.78 seconds. That's forward in time. That's how long it took for something to happen. Okay, so that is not only our best friend. All these equations, which I said were located in the objective section in the Google Drive, but it's also the equation picker on how to actually go ahead and use these equations. And you need to be a little careful if you ever have equation number 5 and you're looking for the time, because it will be a quadratic, and it will be quadratic time. Until next time, though, this is finished. Y'all take it easy out there. In our next video, we're going to be taking a look at some of the weird properties of motion, such as moving up, moving down, left and right, and what happens when an object's kind of in free fall. Okay? So, till then, adios.